Ladies and gentlemen, welcome back to the Ephemeris Podcast, your weekly astronomy podcast. I'm your host, Aphelion, and I must apologize for not getting this episode out on time. This time it was due to a minor illness I incurred on Monday that forced me to delay this episode because I thought I could pull off a same-day upload, but I couldn't. But anyways, that is not what we're here to talk about. We're here to talk about some more news in the world of astronomy from recent times, and we've got 3 articles to do just that today. The first one is going to be about the Radcliffe Wave, the second one is going to be about new moons in the solar system, and the last article will be about cosmic rays. So without further ado, let's get right into these things. The first story, the Radcliffe Wave. So, we've talked about several unusual structures on this podcast before, and unusual structures in the universe specifically, not just unusual structures, because that is quite vague. So some of these unusual structures in the universe we've looked at so far, the Andromeda gas cloud, I guess you could call it, the Magellanic Stream, and I'm sure there are a couple that don't come to mind that we have talked about on this podcast before, but there is another object to add to this list, and it's quite different from the rest. It's called the Radcliffe Wave, and it's a chain of star-forming clouds like many other structures we've looked at. A cool note about the name is that it gets its name from the Radcliffe College, which you'll be familiar with if you tuned into the Henrietta Leavitt episode last season. So more details about the Radcliffe Wave itself. It is 9,000 light years long. And if you remember from last episode when we talked about how long 7 light years can be, 9,000 light years long will become quite difficult to imagine. But not only is the Radcliffe Wave long, it's also oscillating. The region is rising and falling from the plane of the Milky Way. And if you know anything about harmonics, you'll know that creates what is known as a standing wave. So the obvious and first question to ask ourselves here is what creates this situation in space? Like, how do you get this huge chain of star-forming clouds and gas and dust to just suddenly turn into a standing wave? Well, that's the goal of the research paper that investigated the Radcliffe Wave recently. The first thing to understand is that the Radcliffe Wave is a key component of the Orion Arm, which is one of the spiral arms in our galaxy. The structure of Orion has got a high level of star formation and quite a lot of gas, which has kind of been obvious as we've continually described this wave here. But there's an offset between the gas in the arm and the more dense parts of the arm in a galaxy, and that's really the important detail here. We've known about these conditions for a while, but it hasn't been confirmed that this offset was an oscillation until now. So what we suspect has occurred for the oscillation to take place is some sort of cataclysmic event that sort of just triggered the wave that we speak of. The one theory for a possible cataclysmic event would be a series of supernovae that create disruptions that would trigger the event. But then there's another theory that a dwarf galaxy interacted with the Milky Way and created a ripple effect in the region at some point in time. Unfortunately, if we want to go beyond that and kind of understand more about how you just start a standing wave in the Orion Arm, that can only be understood with more research into the matter. So that can be worked on in the future if there are any updates to that. Hopefully I'll find out about it and be able to abbreviate on it in future episodes. But for now, that's what we know. There are some additional and interesting elements here to the Radcliffe Wave that I will discuss before we just let the topic slide. The solar system passed through this structure 13 million years ago, actually, and could very well have made a significant difference in the structure of our solar system. The theory behind this conclusion is that the heliosphere, which you can imagine as the sun's equivalent of our atmosphere, it could have been compressed by the supernova that caused the wave, and that event could have introduced iron and heavier elements into the solar system, which would have made its way to Earth. And the Radcliffe Wave will be important in studying dark matter in our galaxy, which tends to be quite a recurring label that astronomers have used to describe their research. I don't know if it's just to put a label on it or if there's a more significant reason they say that, but that's what has been stated about the study, and so I'll take their word for it. I'm really not in a position to say that they're overusing that line just as a label. So yeah, that is what we know about the Radcliffe Wave, and that's our first article for the day. Let's transition into our second one, which is about 3 new moons that have been discovered around Uranus and Neptune, and the names that will be given to them. Because everyone's familiar with the idea that moons orbit planets in our solar system, I don't need to give much of an introduction here. Just going to get straight into the facts. The International Astronomical Union has confirmed the existence of 3 currently unnamed moons, 1 around Uranus and 2 orbiting Neptune. They were discovered some years back, but they've only been confirmed recently, and that's sort of an element to the IAU's sort of process of confirming and naming objects near our solar system. Time is like, you need a lot of time for these kind of things. And we talked a little bit about this in the article about Zoozve and how it got named, but not necessarily about, confirming the planets or like exactly how much time it takes for this whole process to go through. Another thing that I should mention that may not be clear, the IAU wants names for solar system objects that are mythological. And that's going to be something that we're going to discuss a little bit further here with the 3 moons that we have discovered. So the first moon that we've discovered is a moon of Uranus, and it will be named after a Shakespeare play character, which it's mythological in a way because obviously Shakespeare characters weren't real people, but even if you don't consider Shakespearean characters to be mythological, the naming pattern is still it still exists among other solar system objects. There's some other moons, Titania, Oberon, and Puck are 3 moons that were already named after Shakespeare characters. So it's not unreasonable to keep that trend going. The current name for it is S/2023U1, and some more specific details about it. We know that it's 5 miles across, which is quite small, and in fact, it puts the moon among some of the smallest moons discovered so far. So that's what we know about it. It takes under 2 years for the moon to orbit around Uranus, and it's the 28th moon of Uranus. So yeah, cool stuff going on there. The second moon is a moon of Neptune, and it's around 14 miles in diameter, so definitely bigger. And it takes 27 years to orbit Neptune, which is a really long time. I haven't been around for 27 years, so that to me is already an impressive amount of time. It's now among the 16 moons of Neptune, and one of these moons is the second moon of this article. It's got a orbital period of 9 years and a diameter of 8.7 miles. So the 2 moons of Neptune that we just discussed, they'll be named after Nereids. Hopefully I'm saying that correctly. And it relates to Nereus and Greek mythology. So that one's definitely mythological. I think we can all agree upon that. What's cool about these new moons, besides their wacky names and perhaps their size, is that they were discovered using ground based telescopes. And given the actual radii of the moons, which you just talked about, we know that they're super tiny. And the fact that they're from planets that are so far away, you'd be correct in assuming that the angular radii of these moons would be really small, which makes these moons very difficult to observe. So, what that tells us is that if we were to do ground based telescope observations on this, it would require a very, very powerful image processing method. And the fact that we have that these days is very, very impressive. And that's really the magic behind the observations. It's difficult to discern these moons from ground based telescopes without that technology. So I thought that'd be something cool about the process of finding these three new moons of Uranus and Neptune. And yeah, just something cool to think about. So that's our second story. And now we will move on to our last story today about cosmic rays and where exactly they're coming from, at least the ones that we are currently observing. So we have talked about a lot of gamma ray bursts so far this season. I'm almost running the topic into the ground and should really avoid getting too far into gamma ray bursts that, every single episode or every 2 episodes there is a gamma ray burst article. But we're talking about them again. But instead of looking at them in the same way as usual, where it's like brightest gamma ray bursts, longest gamma ray bursts, we're going to look at gamma ray bursts from the perspective of cosmic rays and how these two ideas relate. So, cosmic rays are high energy particles or clusters of particles that move through space at what we call relativistic speeds. I think that's what that's called. If it's not called that, then they just move through space at nearly the speed of light. So, cosmic rays are subatomic and charged, which gives them a lot of kinetic energy. And when they interact with other matter, they can create chemical reactions that produce unstable isotopes and some other stuff as well. According to our article, however, a large gamma ray burst that was observed in 2022 gave astronomers a great source to look at for cosmic rays. The astronomers looked at the gamma ray burst from 2022 using the Large High Altitude Air Shower Observatory in China. And the name of this specific gamma ray burst is just a bunch of numbers and letters, so I won't bother with the name. But essentially, we used this this observatory in China, and we used it to look at the energy spectrum of this large gamma ray burst. About the observatory itself, it's made up of 5,216 electromagnetic particle detectors, which just shows you the length that some of these observatories have to go to be able to detect things like cosmic rays. The observatory also had like 1,188 muon detectors. They had a 78,000 square meter water Cherenkov detector array and 18 wide-angle Cherenkov telescopes, which is that's almost too much to take in. But that's just the levels that we go to for such minuscule parts of astronomy, I guess I should call it, because cosmic rays are quite small. As we talked about, they're subatomic. So, when the cosmic rays hit or reach Earth's atmosphere, they create showers of secondary particles, which sometimes reach the surface of the Earth, which is how we're able to observe the cosmic rays. We were able to conclude that the detected cosmic rays were due to a massive cosmic ray accelerator near the center of the bubble, which they believe to be the massive star cluster Cygnus OB2 within Cygnus X that would have created what we saw. So within a huge star-forming region in the Cygnus constellation, there's a huge gamma ray bubble, and the emissions coming from it are being accelerated by a massive star cluster. And this is a really cool discovery because of how unknown the origin of cosmic rays are to us. We found a clear source for cosmic rays, and that will really add to our list of possible cosmic ray generators, which I believe supernova is among that list, but not many others beyond that. So it's good to know that we have another origin sort of in the books, and it's just good to know that we'll be able to look at these objects a little bit further to be able to observe cosmic rays. So that is our last article, and that will wrap up the episode today. Hopefully you all enjoyed listening to these fresh articles from the news in recent times. If you did, and you're listening on Spotify, I would sincerely appreciate a follow. And if you are watching on YouTube, I would appreciate a subscribe and a setting of notification to all so that you do get my content recommended in your notification box if you want to return to this channel and watch some more videos that come out in the future. So yeah, that's all I've got to say, and until next week, I will see y'all later. Peace.